speaker, Tariq Al-Kradachi. The title of his presentation is Fire Resistance of Concrete Structures Strengthened with Externally Applied FRP Reinforcement. He is a fellow ACI member and a senior vice president with structural technologies in Columbia, Maryland. Dr. Al-Kradachi has been involved in more than 500 projects involving structural repair and strengthening, many of which have received awards from ACI, PTI, and ICRI. Tariq is an active member of several professional committees, including ACI Committee 440, ACI Committee 562, and ACI 260. Dr. Al-Kradachi has written more than 40 papers and articles on repair and strengthening of structures, and he is a current chair of ACI Subcommittee 562 and ICRI Committee 330. I'll hand it over to him to listen to his presentation.
Okay, good afternoon. So you can see the title. So today what I'm going to try to do is try to connect the dots between different things we talked about this morning. We talked about the fire, we talked about the fire effect on structures a little bit, we talked about polymers and how they behave. We said, there is internal reinforcement and external reinforcement. And we had a few questions also about, okay, so I know all these facts, how do I connect these dots and be able to determine or calculate the fire rating of a structure with or without fire protection? So I've been working with composites for more than 25 years, and I'm on the design side, been on the manufacturing side, on the construction side as well. And being in this profession, I know someone mentioned this morning that you really don't learn a lot about fire protection, fire rating in school, right? We never had any classes on that, so you have to learn on the job. When we started using composites many, many years ago, one of the first questions people ask is, what about fire? I mean, epoxy is combustible material, can catch fire. How is that going to work during fire? At that time, we didn't have a lot of knowledge. And with the years and over time, we start, doing testing, trying to understand the behavior. And we learned that FRP, when it's exposed to fire, it's not going to do well. It's made of polymer that start losing strength pretty quickly. Temperature during fire can reach 1,000 degrees within 7 minutes. That's standard ASTM E119, the curve we looked at this morning. I'm going to show it again later on. So we learned that, okay, we need to provide fire protection. But fire protection, really, how is that going to work with FRP? Because FRP, very low tolerance to high temperature, which means it needs to be something that provide very good insulation properties, which is not possible. Then we start thinking, okay, maybe we need to look at the system. The system, because when you put external fire protection, you're not only protecting FRP, but also you're protecting concrete and steel. And if I maintain the temperature of concrete and steel low enough, then I will have adequate fire rating with or without the contribution of the FRP. Okay? So now I'm going to try to really explain to you how that all work together. And I'm going to go now through a quick introduction about concrete behavior of structures and fire. Then we're going to talk about the effect of elevated temperature on materials. Then how we determine or do fire rating calculations in a simple way, because we can always do complex modeling, but there are other tools available. One of them is ACI 216, and the code that Kevin just talked about has been updated to include lots of additional relationship that relates temperature to strength for materials that can be used for this type of analysis. And then I'm going to talk about the fire protection of RP. How do we achieve that and what kind of evidence we have for that? And if time permits, I'll do a quick case study for a project that I was involved with that included fire protection of structural element strengthened with FRP. So now why are we talking about fire today, right? Because fire is an issue, right? It's being considered as a structural load. And if you look at the statistics, and this is only looking at approximately 10 years, I think there are more updated reports that include last year as well. You can see almost every year for the past 10 years, we get close to 500,000 fires, structural fires every year. Out of these, we get close to 3,000 in death and injuries. And the cost the cost really on average 9-10. Actually, if you look here, you can see the effect of inflation, right there. But the fires, do happen, and do happen to structures, and over the years we've seen many of these fires. The good thing is concrete, and was mentioned earlier, is very good when it comes to fire. It has a good resistance in fire, right? Because it has its inherent properties of providing insulation to internal steel reinforcement. Some of these major fires that you probably heard about over the years, it's Windsor Building. That fire occurred in 2005 in Madrid, Spain. I think this is like a 32-story tower, and when the fire started, I think it's maybe around the 21st story, it lasted almost 24 hours. So in those 24 hours, the only collapse that you see in this photo is this part. 1/3 of the structure was made of steel, was a steel frame. So the steel structure failed, but the concrete structure did not fail, right? I'm sure the structure was severely damaged. Other major fire event is the Address Hotel in Dubai, right? It's an upscale hotel in Dubai near the Dubai Mall. The fire occurred a little bit after 9 p.m. on December 31st, New Year's Eve. I remember it was in the news that year, and I get all these texts from and people I know there. We have an office in Dubai about the fire. And the fire also occurred, I think, around the 20 level, between 16 or 20, something like that. It was an external spotlight. There's a spark from the electric wire attached to it that started the fire. And the cladding, which is something we learn now with this fire and also the Grenfell Tower fire, is that the cladding is really can be an issue. If the cladding is not adequately being tested and verified to not spread fire, it could be a reason that the fire was spread for the building. Also lasted many hours, the structure stood. And actually I was involved in the investigation and the design of the repair for the Address Hotel after that. Lots of concrete work, chipping, shoring that occurred on that structure. And finally, this is the more recent one. We talk about it in the ACI committee, in 216 committee almost every year. We get a report from some members from England on the fire and the investigation. Again, it started through, I'm not sure what's the cause. Some people say it could be a cigarette, someone threw a cigarette from the window, but they had, I think, aluminum with the cladding with insulation material that was able actually to flame. And once the fire started, it's really troubled exterior to the building, almost the full height of the building. Lasted many hours, did not collapse. So historically, concrete structures really been very resistant to failure during the fire events. And I think sometimes we really underestimate how much resistance we get out of fire structures, and the approach we use sometimes in calculation is relatively conservative. The only one collapse over many years, I've done several over the years. Every year there are like a couple of 2 or 3 fire investigations I get involved with as part of, because I'm on the repair and strengthening of structure as part of the business. Buildings, bridges, industrial facilities. I've seen only a couple of years ago a failure due to fire, but it was a precast, pre-stressed element. So less determinate structure, right? It's also, we have bearing and corbels, and one element start falling apart, you may get collapse. And you can see later on, I'm going to show that pre-stressing, in general, pre-stress reinforcement, it's much more susceptible to fire. And I think this morning someone showed that relationship as well. So what happened in concrete? So we said concrete is a very good material, very durable, non-combustible, provide good insulation to steel, internal steel reinforcement, and to the core of the member, right? And it can resist the temperature, high temperature, and doing that by sacrificing some of the moisture inside the concrete, some of the water inside it, and some of the water that we use to create the concrete that starts falling apart. And what happened during fire, it's really absorbed this heat and changed the water into steam, right? As it starts, let's say, evaporating. That is transfer of energy and consume the energy that way rather than falling apart. As the temperature rises, what happened is we can see the steam start building up, right? And this morning we were talking about high-strength concrete versus normal-strength concrete. And we show, I think was that Steve Zoki showed the video, about the explosive nature of high-strength concrete because it's so dense that moisture that is inside the concrete cannot get out. So it really basically creates so much pressure that it explodes the member. And I've seen some of these tests over and over the years where really members can explode under high temperature. These members are high strength. How do we address that? We put fibers, right, in the high-strength concrete, polypropylene fibers. There was a question, how does that work? Well, these fibers, with higher temperature, elevated temperature, will basically disappear, right, burn, and create these, if you imagine, chimneys, tiny micro chimneys that vent the cold steam from the element and reduce that pressure, and that's how they can last. But again, as this concrete start losing this moisture, and after that start chemically change and start degrading, right? But degradation doesn't mean it's not doing nothing. It's really sitting there most of the time. If it didn't spall, it's sitting there providing insulation to the internal reinforcement. And that continues with time until at some point the temperature is so high that you get spalling, right? And when that happens, the temperature of the steel would rise. The temperature of the steel would rise even with the concrete in place, right? Because the concrete would temperature rise, reach the steel. There is some delay between the fire temperature and the steel temperature just because of the cover. But once you lose the cover, start rising significantly. The steel would go through metallurgical changes and then start losing ductility, stiffness, and also strength, right? And with that, as we go through fire, the temperature, the strength start dropping a little bit by a little bit, right? And it keeps dropping until at some point, the strength will be so low that it can barely support its dead weight, right? And then we get collapse. We design what we call, when we do test, UL test, we do for service. And I'll show you the fire load combination, ACI 440 for external strengthening and ACI 562 code. It's really based on a ratio of, try to represent a little bit service with dead and live loads. Here are some of the fires that I've been exposed to. You can see the damage is really not uniform, right? Because fire is a function of the fuel. And when you have concentration of heat, some location you may get significant spalling, some other areas you may see no spalling. So it varies a lot, and I think that's why concrete structure sometimes can last, because the damage is not uniform. Some areas may still be adequately anchored, can last very long. There is moment redistribution, and all different effects that give us some resistance. That's plus we don't have the full live load, right? Even in regular days, we never really have full live load on a structure when we design in service. But you can see between these photos, and I think these next photos, one thing that's common, most of these fires, you can see the damage is limited, more severe toward the top side, right? Why? Right? Because heat rises, right? And if you look at most of them, the floor is pretty good shape. Actually, I've seen many structures where there's a significant damage, but you see the floor is relatively in good shape. This is something that's actually in ACI 216 right now, where it's really clearly say that the top side is not sometimes as critical as the underside. And I mentioned that because this relates to something we do with FRP. Because with FRP, if we want to do fire protection on the underside, we can easily apply spray material or boards or something like that. On the top side, it's not easy to fire protect FRP, because fire protection typically is a soft material, which doesn't make sense to apply on the top side, plus a change in elevations. So I've seen many cases in which even building officials may, based on some of the statement 216 and general knowledge about the fire, accept that fire protection be limited to the underside, not required for the top side. Of course, it's different from building officials to building officials, but you can see that's getting more acceptance now. Other part, of course, I'm not going to cover, but typically when there's a fire damage, right? And before you can go back to the structure, you have to do investigation. If FRP exists on that structure, we typically assume it's all gone. It's doing nothing. It disappeared. So part of the repair is basically as this damage, and you may still have to do repair and have to do strengthening again if you want to go back to the same load level. And there's a lot of details for the assessment part. 562 talk about it. I mean, right now, leading the chapter 10 and 562 on fire, and we included both investigation after fire and describing that investigation. We're going to elaborate on it, but typically what you do after the fire is trying to identify the extent of the fire damage, the depth of the fire damage, and the material properties, right? So some basic things. You can do hammer sounding to see how far the lamination extended into the concrete, right? Because sometimes the concrete looks good, but due to expansion of steel reinforcement, you get separation, right? You can do drill probe, where you basically drill and you start just drilling vertically, and when you start hitting resistance, that tells you the depth of the damaged concrete that need to be chipped and removed. You can take samples of the steel and test them to verify residual capacity if you're planning to keep the steel. And you can do cores. You take cores and do petrographic analysis on it to figure out the depth of the damage if you want. Although in my experience, just simply doing the sounding and the drilling can give you very good indication of the depth of the concrete damage that you need to address. Okay, so let's go back now. I said we're going to try to connect on my side, my presentation, the dots, and see how we deal with this issue of fire and of fire protection of FRP reinforced elements. ASTM 119, right, the standard fire curve that we do. And I apologize, I know I'm going to be mixing units because anything related to fire is most of the time based on international units. In the US, sometimes we convert some of these. I'll try as much as possible to provide conversion, but sometimes you just need to look at the relative value and focus on the concept, because some of stuff I have here not 100% detailed, but I wanted to use some figures to explain concepts. So this is ASTM 119. There's IsoCurve in Europe's been used, very similar to this. Canada, they use similar curve. And I think someone this morning showed a presentation. This is considered relatively on the conservative side. It's almost like an envelope, right? So that's why when we do to 119, it's really very unlikely that to get exceeded. It can exceed it if you have too much fuel. It's not an absolute conservative, but it's conservative most of the time for typical structures. And you can see here, I mentioned earlier, within 7 minutes you can hit 1,000 degrees, right? That's the temperature, the standard temperature in the fire, right? And if you have something external, it may ignite if this temperature exceeds its ignition temperature, let's say. 2,000, 2 hours, 120 minutes, close to 1,000 C, which is 1800 Fahrenheit, and then after that really doesn't increase significantly, goes to close to 2000 Fahrenheit or 1100 C by 4 hours. And I think there was a description this morning, probably it was Steve who said that in most structures are between 1 and 2 hours, which is true. It's very early you see requirement for 3 hours. Some elements, some structures may need 3 hours, but typically 1 to 2 hours. 2 hours is what you see most of the architect put on structural drawings, sometimes even without checking the code. So what happened to the materials? So we're going to look at the materials, how they behave, and then we try to get all these points of data and connect them together into how do I understand overall behavior. This is, I listed here, this has come from Eurocode. This is older version, so I don't know if they changed it. I hear from all our colleagues in Europe, they keep changing it. There's a new version. However, again, look at the concept in here. Is that at 20 degrees C, there's a certain behavior. Oh, sorry, this is the concrete. We start with the compressive strength. You get to the peak, right? This is what we call F prime C, and then after that, you get failure. And as the temperature rises, the compressive strengths start falling apart, right? You lose strength, you lose stiffness of the material, right? So that's keep happening with the concrete, and there are different curves that used to represent those. This is the curve that I'm going to show next that comes from ACI 216, and this is going to change a little bit because even based on my experience is I've seen some evidence that the concrete start degrading at a lower temperature than what shows in here, which is close to 500 C. At 200, 300 C, you can see signs of loss of strength, and I think the new curve in 216 will show a little bit more aggressive loss of strength in concrete. So that doesn't mean when I have that temperature that all the cross-section of the element is falling apart, right? It depends on the temperature. So if, let's say, the outer, let's say 1 inch or 25 millimeter of the concrete reach, let's say, 500 degrees, that means only the outer 1 inch is not contributing to strength, right? Not the entire section. And that keep going with time. So the profile of the temperature through the cross-section is important to understand, because that gives me an idea of what level, what's the remaining residual section that has adequate resistance during fire and which section is falling apart. Now let's look at the steel bar, similar. And I know it's a little bit aggressive, but assume, linear stress strain diagram, and after that I have a plateau, and then there's a hardening. I'm not showing in there. This is the yielding, what we define as yielding, ambient temperature close to 20 C, right? And then it goes to 400 degrees. I start losing stiffness. Strength doesn't degrade a lot, but then strength and stiffness both start dropping as I reach 500 C. The general rule is around 500 C plus minus, or 1,000 degrees Fahrenheit, 1100 in some cases, some people say. You lose close to 50% of the capacity of the steel. Why this is considered critical? Because in general, the assumption is 50% is the minimum you need to at least support the dead weight of the structure, right? So that's why it's considered relatively critical. And then 600, 700, and you can see it start falling apart. If I take the peak of each of these data points and try to plot it again, I can get the curve that represents the strength degradation with temperature. So this is percentage of the yield strength. So let's say it's 60 KSI, 420 MPa steel. Start there and start dropping as the temperature rises, right? So this is mild steel reinforcement. But what that tells me, if I have a tool or a way to determine what is the temperature of the steel, the bars within my cross-section, I can determine what is the residual strength after an hour or 2 hours or 3 hours. And if I know that, I can calculate the capacity after 1 hour, 2 hours, or 3 hours of fire exposure. So this is a very important piece of information. That's why 216 is updating all these curves, because you need these to do what we call rational analysis, rational calculation for fire rating. And if I look pre-stressing steel, a little bit more aggressive, again, there are many different curves within different codes and research. This is just to represent the typical trend, because when we pull the high-strength steel, right, it's called a drone, let's say the 7-wire post-tensioning strands, that changed the molecular structure a little bit and make it more susceptible to fire. Add to that, most of the time, at service they're under stress. May not look significant, I mean, they're close to each other. However, it is really a big difference, because if you look at, let's say, 600 C, while let's say the steel is, close to, let's say, 50%, the pre-stressing steel is close to 30% plus minus, right? So that's mean it degrades much faster for the same thing. That's why, for me, never understood why, the concrete cover is the same for pre-stressed and reinforced concrete, because if I do thermal analysis, I'll find they degrade faster than this. So what happened is that I put all these elements together, right? Concrete section, reinforced, expose it to temperature, the temperature rises with time. What happened? I lose the concrete outer layer by layer in terms of contribution. Steel bar temperature rises, so the strength dropping. So it's keep dropping, and I have the same level of load. So as the section capacity drops, right, what's going to happen is basically the stress within the member or the materials start increasing to a level at some point. The external load effect is more than internal reduced capacity. And in doing fire, we always talk about reduced capacity. At that point, you get collapse of the structural member. That point where it collapses, that is the point we call it the fire rating. So fire rating is at the point at which the existing structural element will fail. That is typically what's referred to as fire rating. Now, good thing is steel recover part of its properties after fire. I don't know what's the new curve in 216 look like. This is some of the data that I pulled from available references. But you can see that the steel, up to 600, 500 degree, let's say, after that when it cools down, it gains back its strength, and most of the time it's above 70%. So always in my head I say, hey, if I don't know, worst case I'm going to assume 70% unless we do some testing and verify the capacity, right? So during fire it drops. When it cools down, it gains back strength, right? Actually, there are some curve for concrete. Even concrete, when it cools down, sometimes it gains back some strength, and it actually hydrates again, start absorbing moisture from the air, and there is a gain strength. But that takes a year to happen. Most of the time, if there's a damage, you start on it immediately. So nobody's going to wait a year to figure out how much the concrete will gain and then go with that. Immediately start chipping back concrete and doing repair and strengthening. Okay, so that was a quick intro to the general concept and how I'm going to connect all these dots. Now I need to look at the FRP, and again there was some discussion about it this morning. I'm just going to try to connect these dots together. So FRP, I think most people here, how many people are familiar with FRP? Okay, good. At least 50-60%. So for those of you who are not very familiar, FRP is fiber reinforced polymer. It consists of fiber that is woven into fabric or just loose fiber that comes in. You can use carbon, glass. There's basalt fiber. There's aramid fiber. But these are the most popular for structural applications. These are mixed with epoxies where you saturate them on site and then glue them to the surface to create this basically cured in place, high strength polymer, very durable, that increases the capacity, right? So that's ACI 440, and its mission is to promote and develop design guide for these components. There are also pre-cured laminate where you just put epoxy on it and you stick it, similar to concept of steel plates. Or there are anchors and bars that also can be used. This morning, Dr. Kudur talked about NSM, near surface mounted reinforcement. That's where you cut grooves into the concrete cover and then glue in the carbon bar. So you provide basically near surface or surface embedded composite reinforcement. So these are the materials. A lot of application, right? That's why we're talking about it, because 20 some years ago it was considered new technology, even though it started almost 40 years ago. Development and research in FRP in the 70s, where you can see that. Now we do them for seismic strengthening for walls. We wrap columns to increase ductility, shear strength, axial load, and use them, around, penetration. So this slab is planned to be cut, maybe for new duct going through it. So they put just FRP to reinforce around this penetration to control, the cracking and make up for any loss of steel, shear strengthening of beams and columns by wrapping. FRP can be on the top side of the slabs, on the underside of the slab. So they're all different configurations. The nice thing about FRP, why it's gaining popularity, is basically flexible material. That you can easily accommodate any shape. You do not have to use heavy equipment or machinery to install, right? And for repair and strengthening, it's really doesn't add lots of geometry. So it's easily to hide and to protect. So all these applications require evaluation of fire, right? And if we look at the fiber, not the composite, just the fibers, the glass fibers and the carbon fibers that are used. If you look at carbon fiber, you can see actually it can go to 800 and even 1,000 degrees. It can turn red like steel and would not lose strength. It's very resistant to high temperature, right? It's actually made under high temperature. And if I look to, let's say, glass is actually is weaker when it comes to the fiber itself under elevated temperature. But this is not really, doesn't matter, right? Because we take these fibers and we embed them in epoxy. So the epoxy is the main component that's going to transfer the load between the fiber and to the structure surrounding them. So the epoxy is the weak linker. When I take these things, put them into a polymer shape, then the behavior will change, right? And we're talking this morning, Scott was asking, what is a critical temperature? That's really something we're trying to understand, because if I look at the behavior of the composite right? It loses strength gradually. So is the critical temperature when it loses, let's say 50%, somewhere in here, which is close to 300-400 C, or is it something else? We keep talking about the glass transition temperature, and I also agree that this is not a really good definition or when the materials start losing strength, because it's not really sudden drop in the material properties. Okay, so I learned this about materials, I learned this about the FRP. How do I do this to look at the fire rating? ASCE 7, and currently also an ACI 562. It's also going into the ACI 440S, which is the code for externally applied FRP that's in progress. There is a design limit or a load combination for fire, which says during a fire, your element with its reduced capacity, supposed to support 1.2 dead, 0.5 live. If you have a roof, then maybe you add another 0.2 for snow, for roof, right? For otherwise, you stick to 0.5 live. So during a fire event, I'm not expecting the full factor load. When I compare this, for anybody external, this is basically in the US. I don't know if it could be different. I know like other codes and standard, New Zealand's and other, they may have different load combination. This could be 1.1 or 1.0, and this could be 0.7, but it's always close. Basically reduced, it's basically dead loads and some portion of the live load, because during a fire, we do not expect to have the full factored live load on the structure, right? And it's an extreme event, so we're trying to design for what is the minimum, or not minimum, what is the expected load on the structure, right? And I just wanted to survive this. 1.2 is conservative, right? A little bit. 0.5 is also considered conservative because hopefully there isn't even that 50% of the live load. To give you a sense, you know, for factored loads, we use in the US 1.2 dead, 1.6 live. I remember there was many studies about the actual load versus the design loads. Office building where we use, for example, 40 or 50 PSF. There are some studies shows a typical office, right, we may have maybe 18, 19. It's even less than half the load we designed for. Right? But there are cases where you have an assembly, lots of people, then you can reach the full live load. Other thing to know, beside different load factors, is the strength is basically has no reduction on it. Like we typically, in the US and some other standards, we use a reduction on the capacity. Right? Because we wanted to account for variability in design, material, installation, errors, stuff like to some degree. It's to account for some variability. Again, this is an extreme event, so my factor is 1.0. So basically, I'm really comparing my nominal reduced capacity due to fire with these loads. So this is important to understand because this is what really fire rating is. Fire rating is when my reduced capacity reach this load combination that you see on the screen. Okay. Other thing to keep in mind, this is not unique to FRP only. This applies to any external reinforcement. So 562, the building, the repair codes, it clearly state that if whether you have external steel plates, with mechanical anchors, with adhesive, or even external post-tensioning, right, that's exposed to fire and not protected. This limit applies to everything. That's basically the existing structure need to support those limits because all these strengthening systems can degrade. Or you have to provide fire protection. You do evaluation. If you don't need fire protection, you don't need to do anything. And another thing to state is you don't always need fire protection. Sometimes you can run calculation and find you have adequate fire rating even if these systems fall apart. Because systems in general may have much higher fire rating than we think. I've run calculation for some columns that we achieved 8-9 hours of fire rating, right? And basically, even if you increase the loads on it and lose all the external reinforcement, you still have adequate fire rating because it drops, right? But it's still adequate. Okay, how we deal with FRP? If I have FRP reinforced, I said that the steel, the strength will drop, right? So I need to use reduced strength of steel. I need to use reduced strength of concrete. Let's say I'm doing shear assessment, not just flexure. FRP, we ignore its contribution to strength, right? That's very clear currently in ACI 440 and also in ACI 562, the repair code. You ignore the contribution of the FRP. Until we come up with FRP that has epoxy that can resist fire, we're going to ignore it. We're going to be super conservative. We're not going to look at critical temperature or TG or anything else. And of course, the phi factor, reduction factor of 1.0. Okay, now I learned the basics, and I know what I need to compare to figure out my fire rating. How do I run the calculations? So we're going to go through this as a way to explain it visually. If I have a beam, I'm assuming simply supported beam, right, applied to uniform load. So we know all what to learn from school, WL squared over 8, that's the maximum moment at midspan under factored load. I'm going to determine the based on the load factor. Doesn't matter which country you are in, you have your own standards, load combinations. This is the moment, factored moment diagram, right? Applied to the member, maximum moment at midspan. And I'm going to provide capacity, provide steel, and design it to give me capacity greater than this demand, right? Now, sometimes we cut down the steel a little bit, but I'm assuming I have the same amount of steel, so I have uniform capacity, right? Ambient temperature, this is what we design for every day. What happens during fire, did I lose the mic? What happens during fire is that what we said is the temperature rises. I lose, could be some concrete section, but more important for flexure, the steel, what's matter? The steel temperature will rise, its yield strength will drop, so my capacity may drop, right? However, I do not compare to the factored load, I compare to a different load combination, a lower load combination. So as long as my reduced capacity is greater than this load combination due to fire that I went over, right? And I have the benefit of its reduced fire, and also I have no reduction on the material. That's another gain. This means I have adequate fire rating, right? But it doesn't happen all the time. If this drops, then I don't have adequate fire rating. Okay, how do I figure out now? That's mean to do this, I need to determine the temperature of the steel so I can figure out the strength of the steel so I can go plug into my shear or flexure capacity calculation, figure out what is the capacity. Well, we have data available in ACI 216 that can help us with this thing. It gives us the relationship between temperature and strength, and give us the relationship with really the temperature profile within the cross section. I can go to that standard. I'm going to jump to it and show you. This is one of the charts that's in the current 216. These are improved, and now we're adding also calculations. Correct, Kevin? We're adding calculations that help you calculate the temperature, not just really profiles that you can see. So this is one of them. This is intended to be for a slab. I'm just going to use this for a simple example. Most of these charts are based on the distance from the outer surface to the centroid of the bar. We don't look at the cover, we look at the distance to the centroid of the bar. That is the depth of the rebar. So let's say I have a slab and it's approximately 1 3/16, 30 millimeter. And at 2 hours, that means that bar is probably the temperature is close to, let's say, 1,000 degree plus minus, 1,030 shown there, or close to 550, 570 C. So these charts can help you figure out what's the temperature of the bar, right? I'm going to use that later on, so keep that in mind. Another way to do it is thermal modeling. And I know we talked about this morning, and Dr. Kudor showed all these models, but it's not that complex anymore. I just purchased thermal modeling software. You can just draw the cross-section, define the material properties, thermal properties, important to know. Apply temperature external, could be one side, two side, ACM 119 could be a standard, and it will calculate for you the temperature profile at any temperature. I can model any beam within an hour, a couple of hours. It's not complex, right? So it's not as sometimes, put to us engineers that this is a complex thing, you need an expert to do it, you need university research to do it. No, things can be done with charts. Now there are equations, and you have also thermal modeling. This is another one. These are some of the charts for beams, for example. And this is looking basically at small section, let's say small quadrant or this quarter of the beam, that basically give you, based on the time, and depend on basically what temperature, you can figure out the temperature profile. So if I have a bar, for example, at this location in here, it would be at 900 C, right, after 2 hours, right, 220 minutes. So I have ways to determine the temperature of corner bar, maybe middle bars. I can also do, again, the thermal modeling that applying the external ASTM 119, the curve I showed you, would tell me the temperature of each of my bars at any time. 30 minutes, an hour, 90 minutes, I can figure all that pretty easily. And here to show you this is actually some of the tests that was published by Dr. Kudor. This is a beam heat test, and we just did a modeling, and you can see between the modeling, you saw with the dots versus the straight line, you can see it's pretty good, right? I mean, the science has evolved. If we understand the thermal properties that include basically thermal conductivity, specific heat, mass loss, density, if you get these parameters and they are ASTM to do them, then you can do any modeling or analysis that you need. And I've done this on multiple different tests where they have data and you can match them pretty good. So, this is to answer a question. Was Amir answered the question about how do you transfer the information from a UL test to building officials? The idea is to move away from the concept if you have to do a test to verify the fire rating. We have the tools to theoretically calculate the capacity, right? So we can simply run the model. All we need to do is to convince the building officials that the models are adequate, can be used for analysis, right? That is the missing gap. How we're addressing that? By working with 216, like 440, I'm being 440, we're pushing 216, and 216 responded to the need of the industry, updating the guide to provide a relationship, and also work on a separate task group rational design document to describe all this thing and provide examples, right? And then this is going to 216. 216 is what? It's part of the IBC, right? It's part of the code. It's a code. Once it gets recognized in the code, then that's really a pathway to be able to do this numerically. You don't have to really run tests each time. Because so if you're done with the steel manufacturer, sometimes they test lots of elements, right? We cannot do that with concrete. We don't have a standard shape. It can be unlimited shape because of the layout of reinforcement, the geometry, the concrete strength. There is no way we can do enough tests to cover all the potential application for concrete. There's another test also show you the same thing. Actually, theoretical most of the time is a little bit above and considered at 1, 2 hours, 3 hours, slightly more conservative, which is okay, right? For a designer, being slightly more conservative, I'm okay with that, right? One thing also I want you to bring to your attention with this chart. This is a modeling for a beam. This is for a corner bar versus middle bar. And I think Dr. Kudor mentioned this. Is a corner bar is exposed to heat from two sides, so the temperature rises faster, which means degrades faster. While a middle bar, or bar really, even second layer, is different than the first layer. So when you do your calculation, you have to determine the temperature of each bar and basically sum them up basically on each contribution of each bar to the capacity. That's also important. Okay. So now, I said, we looked at that slab, for example, and the temperature was close to 1,000 degrees, right? Now what do? I have these charts available in 216. Based on that temperature, I can figure out what's the residual capacity. So, if I started with 60 KSI, 70% that is 42 KSI, or 420, 7% of 420, 280, 285. Megapascal. Now I know the properties of the steel and the concrete. I'm assuming if I'm looking at now flexure, so concrete if it's a little bit weak it doesn't matter because the top is in compression and it's cold. It's not going to affect me a lot. The same thing. It's negative bending may be different. I'm just looking at the example with simply supported beam. Ignore the FRP. And I can run the calculation with reduced capacity, no fee factor, and compare it with the load combination, 1.2 dead, 1.2 dead, 0.5 live, and determine if it's adequate or not, right? So this chart that we looked at, what if I do this with FRP strength, and I found that it's inadequate? Well, that's mean I need fire protection, right? Now, why does this happen? Because two components to the equation, right? I have the capacity and I have the loading. If we're using FRP to repair, we're not increasing the load. maybe sometime it will pass. But if I'm doing strengthening, I'm adding what? Dead load and possibly live load, right? Or live load and possibly dead load. So I'm increasing the demand. When I increase the demand, I lower the fire rating. That's why we, within 440 and 562, we're thinking we need to address the fire, because when you increase the loads on existing geometry, you're basically playing with the fire rating. You're reducing it, and you have to address it somehow, and we need to run calculations. If, again, the capacity I found it's lower than the demand, load factor demand during fire, which is 1.2 to 8.5 live, that's mean I need fire protection. Okay, how do I do that? Well, all manufacturers almost now of FRP, they have a fire protection system that was tested UL with FRP. This morning, Kodor showed the product that he tested for 5. We have system that, we've tested for VRAP, Simpson have, Sika have. So it's now not something that is not available. It is available and can be used to address the fire rating. It's either cementitious, most of the time spray applied. I think some of it can be troweled on. But the idea is we're using a material that is much lower density, so it's more air in it, more insulation, that's basically going to provide protection. That protection is not aimed at protecting the FRP. It's aimed at protecting the steel and the concrete. That's an important thing to understand. And when we're doing the strengthening, we're doing strengthening and then fire protection of the system, not of any components. That is, sometimes people keep talking about fire protection and FRP. Is FRP going to stand fire or not? We don't care, because the code says ignore its contribution. And that's what we're doing. So, can I model this thing? Yes. If you do test, ASTM standard test on that fireproofing material to determine thermal conductivity, specific heat, mass loss, density, then you can go to any software, add additional layer, assign it these properties, apply ASTM 119, and you can still calculate the temperature of the steel, which will improve with the fire protection. This is one of the systems that we use, and you can see most of these systems have much lower. SFRM stands for spray applied fire protection, fire resisting material. Thermal conductivity, you can see it's much lower. Specific heat is higher, which means you need more energy to heat the elements, right? So it's a good thing to be higher. And the density is much lower because there is lots more air in it, and air is a good insulation. And the material that provide insulation, vermiculite, other things are embedded within it, right? So here, for example, a test. This comes from a UL test. The temperature of the steel bar with and without fire protection. So this is without, right? So this is without the fire protection system, 600 C. This is a curve in the middle, right? While the one lower one, it drops less than half the temperature, 260 C, right? And that's what's matter, because if I get this temperature low enough, sometimes I can even maintain the full yield strength after 2 hours and 3 hours. And that's why with this system, you can see from most manufacturers, you can get almost up to 4 hours of fire rating. It does work, right? Because we're addressing the concept of protecting the elements. So what happened with this thing is, right, I'm basically increasing the nominal capacity during fire by protecting the steel and the concrete, right? And I have to keep in mind, even I'm increasing the capacity, but the demand may be increasing if I'm doing strengthening, right? So that's why I have to go check both sides of this equation that we looked at, right? And this is one example. This is a system I mentioned. 1 inch, 3/4 inch can give you up to 3 or 4 hours. And some of these tests I mentioned at UL, we actually instrumented them with thermocouples on the fret location. And the concept is we needed this as a data point to show building officials that we can predict the capacity. We don't need to do the test all the time. So you can see here the thermal modeling, and again, the lines are not exactly on top of each other, but relatively good accuracy. It's actually more on the conservative side. And we can use this to calculate the capacity. This is from one of the beam tests, to give you an example. And again, I apologize, this is in US design values, but look at just the concept in here rather than the actual value. I had the original capacity, 62. with the addition of FRP, it was increased by, that was at 25% to 78. And then the fire load per E119 was 56, which is, we said, correspond to service. Service is roughly 70% of the ultimate, because if you look at load combination, the US 1.2 dead, 1.6 live, assuming they are both dead equal live, so the average 1.4. So basically the service is 1 over 1.4, which is roughly 70%. So of course, if you have the ratio of dead load higher or lower, that's affect really this ratio. So what happened is that after the capacity was predicted, without fire protection is 32. With fire protection, by modeling, is 57, right? And the load was 56. So it says, okay, that means it would last 4 hours theoretically, right? And it did. It did last for 4 hours without failure. Now, we don't know how far, because somebody mentioned it's very expensive to do the UL test. It is very expensive. Every minute you get cost a lot of money because of the amount of the fuel. Once we reach 4 hours, it gets stopped. Could have lasted more, 5 hours, 6 hours, or could be just 1 minute after 4 hours. We don't know. But it passed. So the theory does work, right? Every time we apply it. Fire protection system, most of the time, it's mixing of, different cementitious component with water, and you can spray apply it. You apply it to the FRP. I mentioned the thickness between 3/4 inch and 1 inch, so it's not a significant change to the structural element, but it's enough to provide adequate fire protection. Here's some of the photos of elements that have been spray applied with FRP. Okay, so now, what if with all this fire protection, whatever, I cannot make it work? Well, maybe then FRP is not the right solution in this case, right? One thing to mention is that I want everybody to keep in mind is ACI 440 has a limit on the strengthening. To keep FRP as what we call supplemental or secondary reinforcement. That means we're only increasing the capacity by plus minus 40%, depending on the dead load to live load ratio. So most of the time we're not increasing the load significantly, and that's why most of the time if we have reserve in fire rating based on detailed calculation, maybe okay, and you don't need fire protection to FRP. But sometimes you find you need it. In these cases, if you exceed the strengthening limits, or if you cannot make it work, you go to the conventional solution. Enlargement, add steel, roughen the surface, dowel in, form, and pump some concrete. We do this all the time. It's very, very common. We use external post-tensioning, many different techniques. Okay, so let me now show you an example of a project that we worked on with FRP strengthening. So this project, required strengthening, shear and flexure, the changing load, adding dead load, live load. The consultant specified the required capacity, increasing capacity, and said, I need to our fire rating, apply fireproofing everywhere. Well, the owner, university, said, well, that's too much cost. Really, we need fireproofing everywhere, because fireproofing in practicality can double the cost of the repair. It's almost the same cost of putting a FRP and putting fireproofing on top of it. You still have labor and work on every square foot, etc., and materials. So we said, okay, let us go through the analysis, and we talked to the building officials at the time. We said, okay, this is the approach, here's the evidence. Are we going to run through this calculation, show you one by one, capacity versus demand after 2 hours? If it passes, we don't need fireproofing. If it fails, we'll apply fireproofing. And sure thing, we went through this thing, and by running the calculation, we found only 30% of all the elements require fireproofing. Okay? So it wasn't required for all of them, right? But I want to show you a critical one that required fireproofing. And this is an element where we have really small joists, or waffle slab joists in some cases. And the reason why it was really critical, because it only have 2 corner bars. And corner bars, I mentioned to you, they're more susceptible to heat, right? Because heat hit them from 2 sides, so they temperature rise quickly. So we're concerned with this, but sure thing, it did not pass. You can see here, these are the dimensions. So this is 28 inches in depth, 2 number 9 bars, and then here the U1, U2 represent the centroid to the bar. So these are the properties, and again, I only have it in US numbers, so just look at the concept and the ratio of the strength. And we went through the process, same process that I mentioned to you, right? We calculate maximum temperature, which is ASTM 119. We know what's the temperature at 2 hours, right? So we take that temperature and run it through either by curves, through 216, or through modeling, and calculate temperature of each bar, and then calculate the yield for the higher temperature, and calculate the capacity, and compare it to the demand during fire of 1.2 dead, 0.5 live. So these are the numbers for that specific beam. The dead load was close to 85, live load close to 80. So when you go through load combination, during fire, the demand is 144 kipfoot that I need to withstand during fire, right? When we run the calculation for those bars, the temperature, again, you can see that corner bar rise to almost 1200 degrees Fahrenheit, 640 C, right? At that temperature, the curve is very sharp, and then the yield drops significantly. So this is what? This is less than 25%, right, of the capacity of the steel bar. So they would not really pass. And even if we ignore the FRP contribution, so this would be the capacity, right? Close to 60 compared to the demand of 144 would not work, right? So this is an element that would not work. So we did the same thing with fire protection, apply the fire protection, rerun the analysis, and show it would stand, right? Was able to stand. I don't think I added that. Unfortunately, I should have added that. I was just thinking about it this morning. The calculation with the fire protection to show the difference, how it's reduced the temperature of the steel bars and increase the yield strength. So once that was done, all these specific elements, this is before, wrapped with FRP, and then after it was sprayed with the fire protection. Fire protection, most of the product I know in the market, gray in color, so it's more like a concrete look to it because it has cementitious material. So it would blend in relatively well with the existing structure. Okay, so that's my summary for the day. I just wanted to make sure that I was concerned that people are going to talk about all different things, but no one's going to talk about the process. How would those who are doing engineering deal with this thing on day-to-day? And this is the concept that 562, 216, and 44 is now pushing for. Do evaluation, rational design approach. 216 taking the lead on taking this rational design approach, put it into a procedure with curves and relationships and design example to allow engineers to be able to determine fire rating. So no one has excuse not to use FRP because they say it doesn't have adequate fire rating. You can run the calculations, all right? Okay, any questions?